Time to get revived. And in this question, we have an interesting use case of the periodicity of functions. To start, we wish to show that the wave function of a particle in the infinite square well returns to its original form after a quantum revival time T equals 4ma squared over pi h bar. That is, psi x of T is equal to psi x of 0 for any state, not just a stationary state. Part B, what is the classical revival time for a particle of energy E bouncing back and forth between the walls? Part C, for what energy are the two rival times equal? Now there's worth mentioning here that the author has a footnote on this question, and it says that the fact that the classical and quantum revival times bear no obvious relation to one another, and the quantum one doesn't even depend on energy, is a curious paradox, to which he sources a paper, and I will have that down below because I think it's an interesting read. But nonetheless, let's dive into this question. So to start, it might be helpful just to write out what the general solution for the time-independent Schrödinger equation is, in the case of the potential being the infinite square well, which we found pretty easy with the linear combinations as a summation. So now that we have this written out, and we see that we have h bar here in the denominator, plug in e in, so we have the most general case, and you see that the h bar in the square and the square e term cancels with the h bar in the denominator here. We write this out because what we're trying to show now is that for any state, not just stationary, that the goal is to show that psi x of little t is equal to psi x of little t plus big T, i.e. we return back to whatever the state was at any time t. So with that, let's go ahead and plug this in and try to simplify this expression down. Color coding for little t green, big T blue. We see that if we plug that time increment into the exponential, we can use the property of exponentials, and since they're adding here, we can multiply here. So now our focus is to go to the exponential term here and focus on whatever kind of periodic nature that it might have. So let's go on and see what else we can do. Alright, so now that we have the exponential split, let's go ahead and plug in the capital T that was given to us. Note that there's a lot of common factors here, so let's just cancel them away safely. We have 2ma squared in the denominator from the energy term. That cancels with a factor of 2 in the 4, and the ma squared here from the capital T. Similarly here, we have h bar canceling with h bar, and we have a factor of pi canceling with the factor of pi from the energy. Alright, so now that we can simplify this down, the summation, keep all that first exponential and coefficients together, we see that we have a leftover factor of 2, a leftover factor of pi, and then the n squared here. But here's where we get a cool little observation. And here I state that this is equal to 1 for all n that are an integer. Reason being is because of Euler's identity, which we've seen before. So here, let's quickly note that the e to the I theta is equal to this expansion. We've seen that before. But we know that cosine is 2 pi periodic, and sine is 2 pi periodic. So the periodicity of e to the I theta plus 2 pi, you plug that all through, you see we get back to e to the I theta, meaning that this exponential here is periodic for any multiple of 2 pi, and since n squared is an integer, because n is an integer, and if you square two integers, you get an integer, we know that this whole thing is 2 pi periodic based on the Euler expansion here. So we like that. And so we know that that's equal to 1 for everything, because sine at 2 pi is equal to 0, and cosine of pi is equal to 1, so the whole thing equals 1 for every multiple of 2 pi. Wonderful. That's the periodic nature we were looking to prove, and because of that, we multiply everything here by 1, and sure enough, we get back to the starting wave function we had, which was psi x of t. Now, without giving the capital T here, all we'd have to do is look for where this thing becomes periodic and then back solve. So either way, either direction you go, it works. This is just a great check, and this is what you have to do for all periodic testing. Um, Periodicity is really big in Fourier analysis, so that's a hint for later if you haven't realized Fourier is a part of this theory. But moving on to part B, the classical revival time is the distance it takes the particle to go down the well and back. So if we're looking at a ball, it has to go to the end of the well, bounce back. And of course, we need to know if we want a time, we need to know the distance and the velocity and divide the two. And that's what we do here. So now that we have both the distance, since we have to do two lengths of the well, the length going forward and the length coming backwards, we get 2 over a, and then of course the particle's speed. But we know we could find the speed from the kinetic energy since the particle is moving, and the potential is 0 in the well, so we're good there on all chords. Multiply the 2 over, divide by m, so we get 2e over m, take the square root, positive of course. And if we plug this v in here, we get 2a over the square root here. This just comes down to multiplying by the reciprocal of the root. That's how we get m up top, e in the denominator. But because we have a big 2 out here, we could push that into the radical via using 4. So what we have is 4, this turns into a 4, this turns into 2. 4 over 2 leads us to this 2 here. And that's how we end up with our simplified radical. No big deal, but definitely cleans it up. Now, the curious part about C is that the two rival times are equal when clearly the quantum time and the classical time are set equal. So we start with the blue and the green, and we just solve for E. What we notice here is that after the cancellations, of course, you take you square both sides, take the reciprocal. That's what we end up with here, 2m from here. All this thing squared in the denominator that replaces it when we cross multiply over. Noticing, of course, that we have 2m canceling with 16m squared. Factors, of course, so we're left with 8 here and 1m. Let's note here that this is a great candidate to be simplified even further using the quantum energy condition, since in an infinite square well, we have En is equal to n squared pi squared h bar squared over 2ma squared. 8 is 4 times 2, so we have 2ma squared in the denominator, checks that off. Pi squared and h bar squared, we have that. That must mean that n needs to equal 1, and that's what we see here. N equals 1 for E in the case of what we have here. And that simplifies things down tremendously, but it is interesting because in the discussion of the free particle, we noticed that the speeds, the classical speed and the quantum speed, were off by a factor of 2. So in the square, that factor 2 becomes 4, and so at least we have some self-redundancy here. Pretty cool, but definitely can be a headache if you're not used to seeing these things. But the classical world and the quantum world, man, they contrast pretty heavy. Thank you for watching. As always, until next time, happy learning.